Hello everyone and welcome back to another video where we will briefly introduce decision trees to machine learning. So like previously we talked about clustering algorithms as well as regression algorithms used as a means of making a boundary between one class and another class or one class and several other classes. Decision trees are another way we can do that. I think they're a pretty fun type of algorithm once you get to understand it. And so we'll jump right in with it. So the way a decision tree works is that it learns a hierarchy of if-else statements that lead to a decision. So you can see this little graphic I have here on the right. It looks like a tree if you're familiar with different software development practices. This looks like a typical binary tree that you might see when you're coding different data structures. But the idea here is that your data will input from the top here to the top node, and given different attributes of that information, we can make a decision. So, like for example, at this first level here, I have a true or false. This could be: are the eyes blue? True or false? Is it greater than 17? True or false? And based on that decision, it will then take a path one way or the other, or then depending on the data that you're learning from, you may have more decisions to make until you arrive to one of your final classes. So in this example here, in total, I have 4 different classes. Okay, so the tree acts as a model to distinguish between a number of classes using a certain number of features. And in the way I can describe the classes at the very bottom, you could say I have different features at the higher levels. Right? Whenever I have to make a decision, so we could count this one as well. Whenever I have to make a decision, true or false, then I'm using a feature. Is this feature present or is this feature absent? Right? That will allow me to make my decision and then traverse deeper into the tree. So another way you can word this is that to learn the decision tree means to learn the sequence of if-else questions that gets us to the right answer. Right? Every time that we reach one of these decision nodes, we have to ask, is it greater than or less than? Is it equal to or is it not equal to? But interestingly enough, of course, your types of problems will change from time to time. The type of data used to represent your problem will also change. Decision trees, they make most sense, at least in my opinion, to explain them by using qualitative data. Is it green or is it blue? Is it high or is it low? Is it rainy or is it sunny? But oftentimes when you're using this, you'll get the most use out of them, most bang for your buck, by using them with continuous numbers. So very similar to how your regression algorithm can best predict off of a continuous data set. That you'll also see that behavior in decision trees as well. So these questions that we're asking every time we reach one of these boxes, they're also known as tests. Right? You can test to see if this feature is present or if this feature is absent. Because oftentimes you're using quantitative data, using numbers, continuous numbers, you'll see, once your algorithm learns, you'll see things like, is this feature larger or smaller than a certain value? Right? The algorithm finds which tests reveal the most informative detail. The algorithm finds which tests reveal the most informative details of the data. Right. So all these tests or questions that we're asking throughout the whole tree, the algorithm is actually learning that. That's not something that we're creating ourselves, because this is machine learning. If we were creating it ourselves, that is something you can do, but it's not machine learning. It's just software engineering at that point. So that's what makes this really interesting, especially when you're using quantitative data, because the representation of all the features is relatively uniform. The learning algorithm will actually figure out what are the best tests to add at these nodes. Right? So let's say you had a data point that had 3 features, and each feature was represented by a number. Right? And you could say feature 1 was equal to 10, feature 2 was equal to 50, and feature 3 was equal to, say, feature 1 is equal to 10, feature 2 is equal to 50, and feature 3 is equal to 42. I should get better at writing these out so you can see this, or instead of me just talking. So, when you're going through this decision tree, you might reach the first test, and it will be asking, is feature 1 greater than 13? And at the next level, you might have, is feature 2 equal to 50? And at your final node, this tree doesn't represent that in this case, but a final node, or alternatively, if you did match that F1 feature 1 was greater than 13, you might have a different decision to make here. Let's say that. And that last one was, is feature 3 less than 96? And if we were to take that, so the first one is feature 1 greater than 13, right? We're over here asking that. Is it greater than 13? Well, we see our value is equal to 10, so it's actually less than 13. So that means we go along the false route. So now we're in this box, okay? And this box here, we're asked if feature 3 is less than 96. And we see our feature 3 is equal to 42, so this is actually true. So then we take the true branch, and then this data point represented by these 3 numbers would end up in this class right here. Right? So that's sort of the decision tree, the process, the flow. And the cool part about it, the coolest part, is that all these decisions that have to be made are actually learned by the algorithm. And it's pretty cool. So won't get into the math once again, but just know that this is the way that this algorithm learns, is that it's a recursive process of finding informative tests. Just to quickly illustrate that, and so the strong point of decision trees, I think, is when they're visualized, either in this format where you can see how the flow of decisions are made, or when you can actually see the distinguishment between the classes. And so you can't see my hand in the pencil writing here, but let's say I were to hold it horizontally, right, and then just move it down along this data point. You can see there's a pink class and a blue class, right? And let's say that I wanted to do this one right here. Let's say I wanted to take the horizontal line that gave me the most informative information, and in this case that would be getting as many pink data points on one side and as many blue points on the other side. Well, if we look, we'll see that this line right here is probably the one that can separate the blue class from the pink class as best as possible. So let's just leave that one. Okay. Now we also see that this isn't perfect. There's still a couple pink nodes below and a couple blue nodes above. So, what we've done so far by drawing this one line is making one decision, when in reality we can have multiple levels of decisions. So now let's say I want to pass a vertical line. Actually, is that color? Let's pass a vertical line over the data set. Okay. Now, here we want to have as many pink on one side and blue on the other side. And I think that one is going to be this line. Wait for it, right here. Okay. So now we can actually combine these two because we're following a tree. So if a decision at level 2 or a test at level 2 is met, that means the test at level 1 was met. Right? If it's on one side of the yellow, it has to be on one or the other side of green. So we can look right here. We now have a combination. then you see our decision tree gets a little bit better because now we have the condition to be a pink class means you have to be above the green line and to the left of the yellow line. That combination together will encapsulate this entire area. Right? But you can see we still have a couple stray blues here, so we're not quite done yet. There's too much there. That's that. And so let's pass one more line, one more level of decision making, and that will be this red line here. Right? We will do the same thing as we did with the yellow line. Okay? And the most informative one here, I'll say, is going to be this last red line right here. Okay? And again, we can combine them. Okay? And now you can see a much better distinguishment between the two classes here. So everything that is below the green line to the right of the red line is going to be, and also to the right of the yellow line is a blue class. Right? And everything above the green line to the left of the red line and to the left of the yellow line is going to be the pink class. Right? And that's sort of how our decision tree will learn. If you want to experiment with this, try it out a little bit yourself. I recommend drawing something just like this to start with and seeing how you can use a number of lines to distinguish between the two. Right? And using this line practice, using this line practice it's the easiest way to visualize how this algorithm uses the decision trees to classify based on numerical data, because sliding a line along here is as if you're saying, is it greater than this x value, greater than this x value, greater than this one, greater than this one, or less than, right? In the same way with the vertical lines. What we just drew here is representing data in a two-dimensional space. So just know that if you have a high dimensionality of your data, it's doing the same exact algorithm or procedure, but in multiple dimensions. Okay. Once trained on a new data point, enters the decision tree. So yeah, once you have those decision lines, so let's draw a generic one here. It looked a little something like this. Once you have a new data point entering, let's say we draw it in red, the data point happens to be up here. Well, we see it's above our big line boundary, so it belongs to the pink class. Right? In the same way, if any data point enters in, that's exactly how it gets classified. So with that, I hope you enjoyed this introduction to decision trees, and in the next video we'll talk about a little bit of the extended functionality of decision trees as well as some of the drawbacks.